Welcome, travelers, to Adventures in Security. In this video, we explore taking an engineering approach to secure network infrastructure design. The video script, along with the bibliography, is available at the link in the video description. In this video, we're going to design a secure network the way an engineer would design a bridge. We start with requirements. We model the system. We analyze the risks, and only then do we pick technologies. By the end, you'll have a repeatable method. You can apply to campus networks, data centers, hybrid cloud, or even a small business with a few sites. You'll also hear a mini case study where we walk through the process for a 500-person organization. As we go, keep one idea in mind. Security is not a box you add at the end. Security is a property of the whole network. Topology, identity, configuration, monitoring, and operations all work together. When any one of those is weak, attackers root around your best tool. So let's build a mental toolkit. The steps, the artifacts you should produce, and the design decisions you should be able to justify. Think of this as a classroom lecture you can replay whenever you're facing a new network design problem. When I say engineering approach, I mean a disciplined life cycle. Step 1 is defining the problem. What the network must do, what it must protect, and what constraints you have. Step 2 is modeling. Draw the system, the data flows, and the trust boundaries. Step 3 is analysis, threat modeling and risk assessment. What can go wrong, and how bad would it be? Only after that do we move to design. Choose an architecture, segment the network, and select controls. Then we verify and validate. Reviews, testing, and evidence that controls actually work. Finally, we operate and improve. Monitoring, incident response, patching, and learning from failures. Engineers also produce artifacts. For secure networks, the deliverables are things like a logical and physical diagram, a data flow diagram, a zone-to-zone policy matrix, a risk register, a control mapping to a framework, and a test plan. If you can't point to these artifacts, you're probably relying on tribal knowledge, and that doesn't scale. Let's walk through the life cycle, one step at a time. We start with requirements, because requirements drive every later decision. First, identify the mission and the crown jewels. What data or services would hurt the organization most if they were stolen, altered, or unavailable? Examples include customer PII, payment data, manufacturing control systems, or even just identity infrastructure like Active Directory. Next, capture the use cases. Office users, remote workers, contractors, APIs to partners, and admin access for IT. Each use case becomes a set of network flows you must allow. Then write security and reliability requirements as measurable statements. For example, remote access shall require multi-factor authentication. Or, critical applications shall tolerate a single device failure with no more than 60 seconds of disruption. Finally, record constraints, budget, latency limits, legacy protocols, staffing, and the organization's risk appetite. Some risks will be accepted, but you want that to be a conscious, documented decision, not an accident. When requirements are clear, the rest of the engineering process becomes much easier to justify and to audit. Now we model the system. In networking, modeling means making the invisible visible. Start with an inventory. Users, endpoints, servers, network devices, cloud resources, and third-party connections. Add data classification. Which flows carry public data, internal data, or regulated data. Next, draw data flow diagrams. I like to separate north-south traffic into and out of the environment from east-west traffic, which is lateral movement inside the network. Attackers love east-west paths, so we have to see them. Then mark trust boundaries, A trust boundary is where the security assumptions change, like Internet to DMZ, user network to server network, corporate to cloud, or production to management. Every boundary becomes a candidate enforcement point. Finally, list dependencies and assumptions. Your identity provider, DNS, certificate authority, time synchronization, and management tools. These shared services are often the real single points of failure. If you leave this slide with one takeaway, it's this. A good diagram is a security control because it prevents you from protecting the wrong thing. With a model in hand, we can do threat modeling and risk assessment. Threat modeling asks, how could this design be abused? You can use structured methods like STRIDE, spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege applied to each data flow and trust boundary. You can also map likely attacker techniques using resources like MITRE ATT&CK. Then we translate threats into risks by estimating likelihood and impact. Likelihood is about exposure and attacker effort. Impact is about business damage, financial loss, safety, downtime, legal penalties, or reputation. The output is a risk register. Each risk has a description, affected assets, a score, an owner, and a treatment plan. Treatment options are classic engineering trade-offs. Mitigate with controls, transfer with contracts or insurance, avoid by changing the design, or accept with explicit sign-off. A practical tip. Prioritize attack paths, not isolated vulnerabilities. For example, phishing to stolen credentials to VPN access to lateral movement to domain admin is an attack path you can break in multiple places. Now we're ready to design with purpose. Before we pick tools, we anchor the design on principles. First is zero trust thinking. Don't assume anything is trusted just because it's inside the network. Verify explicitly using strong identity, device health, and context. Second is least privilege and default deny. Only allow the flows that your requirements demand and deny everything else by default. Third is defense in depth. Assume one control will fail, so you layer protections, segmentation, authentication, encryption, endpoint hardening, and monitoring. Fourth is minimizing attack surface, reduce exposed services, simplify paths, and remove unused protocols. A principle that's often missed is securing the management plane. Your admin interfaces, automation accounts, and out-of-band access are the keys to the kingdom. They deserve their own network, their own identity controls, and extra logging. Finally, build invisibility. If you can't see authentication events, DNS, firewall decisions, and endpoint alerts in one place, you will detect attacks late and respond slowly. Principles act like guardrails. They keep the design consistent even as the environment changes. Now we translate principles into topology using zoning and segmentation. Think in zones. Internet, DMZ, user networks, server or application networks, restricted data zones, and a dedicated management zone. Each zone has a different trust level and a different set of allowed flows. The engineering trick is to make policy explicit. Create a zone-to-zone matrix that lists exactly which source zone can talk to, which destination zone, on which ports, and for what business reason. If a flow isn't in the matrix, it doesn't exist. For north-south traffic, the DMZ is your airlock. Public-facing services live there, and only the minimum required traffic is allowed inward. For east-west traffic, use microsegmentation. Separate workloads by function and sensitivity, not just by IP address. In cloud, security groups and network policies can enforce this same idea. Also separate environments, production, development, and testing, and isolate third parties, and IoT devices. Segmentation isn't about making the network complicated. It's about limiting blast radius when something goes wrong. With zones defined, we choose controls to enforce the policy and reduce risk. At the edge, typical controls include DDoS protection, a web application firewall for HTTP apps, next-generation firewalls for rule enforcement, and secure DNS filtering. For remote access, modern designs often prefer zero-trust network access or a hardened VPN, always paired with MFA and device posture checks. Internally, focus on detecting and blocking lateral movement. Host-based firewalls, IDS/IPS, where appropriate endpoint detection and response and strict egress controls so compromised systems can't easily call out. Cryptography is part of network design, not an add-on. Use TLS for application traffic, and use IPsec or equivalent for site-to-site links when needed. Plan key management, certificates, rotation, and who can issue them. Don't forget, secure infrastructure features. Strong routing protocol authentication where feasible, DHCP snooping and ARP protections on switches, and hardened management services. Finally, baseline configurations matter. Start from benchmarks like CIS and map your chosen controls back to a framework so you can explain why each control exists and what risk it addresses. Identity is the new perimeter, so we design it into the network. Start by choosing a clear source of truth for identity, an identity provider that supports MFA conditional access and good logging. Then extend identity to the network layer using 802.1x for wired and wireless access. That lets you authenticate users and devices before they ever reach a production VLAN. For devices, use certificates and device posture checks. Things like OS version, disk encryption, and EDR health. The idea is simple. A managed laptop should get different access than an unknown device. For network administration, use centralized AAA such as Radius or TACACS Plus, and put privilege access behind a jump host or privilege access management system. Log admin sessions. Rotate credentials. Prefer just-in-time elevation over permanent admin rights. For application-to-application traffic, use service identity, often mutual TLS, so that who is calling is verified, not inferred from an IP address. If you design identity well, segmentation and firewalls become much easier because policy can be based on who and what, not just where. A secure network must also be resilient and observable. Resilience starts with availability engineering. Redundant firewalls, redundant links, diverse internet providers, and tested failover. But be careful. Redundancy can increase complexity, so you validate it with drills, not assumptions. Next is containment and recovery. Keep backups isolated from the production network and protect your management plane so an attacker can't disable defenses. For critical services like DNS, identity, and logging, plan capacity and recovery steps because outages there can paralyze incident response. Observability means collecting the right telemetry. Authentication logs, firewall and proxy logs, DNS queries, DHCP events, endpoint alerts, and flow data like NetFlow. Centralize them in a SIM, tune alerts to your environment, and connect alerts to runbooks, step-by-step response procedures. Finally, design for denial of service and abuse, rate limiting, upstream DDoS services, and clear escalation paths. In engineering terms, you're closing the feedback loop. You can't control what you can't measure, and you can't defend what you can't see. Engineering always ends with verification and validation, and security is no different. Verification asks, did we build it right? That includes configuration reviews, rule-based reviews, and checking that controls match the zone-to-zone matrix. Validation asks, Did we build the right thing? That's where threat modeling and requirements come back in. Build a test plan that includes connectivity tests for required flows, negative tests that confirm blocked flows, stay blocked, failover tests, vulnerability scanning, and periodic penetration testing. Consider purple team exercises, where defenders and testers collaborate to confirm that detections fire and that response steps work. Automation helps here. If you manage firewall rules and cloud security groups as code, you can add automated checks. No inbound admin ports, logging enabled, default deny, and only approved egress. Then track metrics that matter. Mean time to detect, mean time to respond, patching SLAs, and control coverage for your highest risks. After incidents, or even near misses, feed lessons learned back into requirements and design. The goal is a living system. The network gets safer over time, instead of slowly drifting into insecurity. Let's apply the method with a mini case study. Imagine a 500-person company with a headquarters, 3 small branches, Azure workloads, and several SaaS platforms. The crown jewels are customer PII and payment data, and the business requires 99.9% uptime for the customer portal. Requirements first. Remote work is mandatory, so remote access must use MFA. Regulated payment systems must be isolated, and operations need centralized visibility. Modeling next. Draw flows from internet users to the portal, from employees to SaaS, from branches to HQ, and from apps to databases. Mark trust boundaries at the internet edge, the DMZ, the user-to-server boundary, and the on-prem to cloud boundary. Threat modeling highlights credential theft, ransomware lateral movement, and cloud misconfiguration. So in design, we create zones, internet to WAF/NGFW to DMZ for the portal, an application zone, a restricted database zone, separate user and guest networks, and a lockdown management zone. Controls enforce the design, ZTNA or hardened VPN with MFA, 802.1x for access, microsegmentation for servers and cloud security groups, PAM for admins, and centralized logging into a SIEM. Finally, we validate with rule tests, tabletop incident exercises, and failover drills. The deliverables are the diagrams, zone matrix, risk register, control mapping, and test evidence. Let's wrap up with the big takeaways. Secure network infrastructure is not a shopping list of products. It's an engineered system. You start with requirements, you model the real flows, you analyze threats and risks, you design zones and controls that match those risks, and you verify with testing and evidence. Then you operate, measure, and improve. If you're new to this, start small. Pick one critical application, draw its data flow diagram, and build a zone-to-zone policy matrix. That one exercise will reveal surprising trust assumptions. Next, invest in 2 things early: identity and visibility. Strong authentication plus good telemetry will improve almost every other control you add later. Finally, keep your documentation alive. A diagram from last year is a liability if it's wrong. Treat diagrams, risk registers, and control mappings as version-controlled artifacts. I've included key standards and guides in the description, so you can go deeper. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.